So I'll be talking a bit about our new FAST.Farm tool. So for those of you who don't know what FAST.Farm is, it's nothing to be surprised by because we actually haven't released it publicly yet. It's coming very soon, but it's all based on our FAST software and other work we've done on wind farms. And the reason I'm out here is because I've been invited to be an external examiner for soon-to-be Dr. Jonkman, and so very excited to have that this afternoon, and best of luck to you. Normally, I speak to people that are quite experts in wind energy, but just as background, so in the U.S., probably until about 5 years ago, the focus of our research effort was all on turbines. How do we make turbines bigger, better, more efficient, more cost-effective, more reliable, and so on? About 5 years ago, what the industry basically asked us to do is, as you're developing more advanced technology, you're coming into our space where turbine designers are dealing with, and we don't want if I'm from GE or Vestas or Siemens, I don't want you to be mucking around in my space because I want my own IP and my own things that are advancing technology. So they asked us, what we would like you to do at NREL is kind of look a little farther out and solve the big grand challenges that we see in wind. And one challenge that we see is so instead of designing turbines to be optimized for one turbine, how can we optimize the whole wind farm itself collectively as a unit, what we call a wind plant? And can we do things novelly in a wind farm setting that you wouldn't do if you simply optimized every turbine individually? And so we said, well, that's a very interesting problem. We have nice big supercomputers that we have access to at NREL, so let's try to really understand this problem of if you have a mesoscale environment, you have flow over the terrain regionally, of course, that feeds down into local scale effects that are driving the flow through wind farms. There's an atmospheric boundary layer to turbine interaction. And what can we do if we start understanding this whole environment better? Could we place the turbines better in the wind farm? Can we control the turbines uniquely? One of the novel strategies we're looking at, which I'll talk about briefly, is called wake steering, where if you take a turbine, normally you want to always yaw the turbine directly in line with the wind to maximize the energy capture. But if we say, when you do that, what happens is it creates a large wake behind the turbine, and so the next turbine behind it gets much less energy than you would for the free street turbines. And so what happens if we simply yaw this turbine here, and then what happens when you yaw, you have a skewed flow. The thrust is kind of pushing the wake in the opposite direction that the rotor's pointing, and you can then basically skew that flow around the turbine. And so while you may sacrifice a bit on the upstream turbine, you'll get more than that back on the next turbine. So by using things like wake steering, we can then improve the overall energy efficiency of a wind farm by basically doing nothing. And so the question is, when we start doing this, and we've shown this both in simulation and also in prototype tests where we take a full wind farm, we take a corner of the farm, we start applying these wake steering technologies, and clearly we see relative to the rest of the wind farm where we're not doing this, the energy is going up. But always the question is, well, what do we do? If we're purposely yawing turbines, we're inducing asymmetric loads on our turbine, and of course fatigue life and so on is critical. And so how do we really do this in design? And that's what we're trying to do here with our FAST.Farm tools. I want to be able to not just design one turbine, but I want to be able to understand how these turbines interact with each other and design the whole system holistically and be able to predict the ultimate fatigue loads that the turbine's going to experience. And so when we started this project about 3 years ago, there were a number of tools out there already. Florus, if you're familiar with these tools at all, I don't know if anyone is, but Florus is a basic steady state model. So very, very simple wake model. It can run, instantaneously, effectively, but it's completely steady state. So we can predict mean effects, average power that a wind farm can produce for a given wind condition, but it can't produce structural loads out. So we use a tool like Florus to do like a wake steering optimization. We say, well, if I have these 36 turbines in this wind farm, how can I best arrange the yaw configurations or thrust to best optimize the performance of that farm? But it won't tell you anything about loads. If I jump over to the next level, and what Jonkman is going to be talking about this afternoon is very high fidelity large eddy simulations, where you're really trying to resolve, and this is a large eddy simulation from our SOFA tool, We're really trying to resolve the physics of the flow with basically a computational solution. These are very, very nice simulations. They're also very, very expensive. So the simulation like this, where you're analyzing basically all the turbines in the wind farm, that probably takes a couple weeks to run. So while you can then learn a great deal of insight of what's going on in the flow, you're not going to do that in really a design loop process where you're trying to optimize the turbines. And so, and then in the middle, and that's where I focus my effort, is on what we call engineering fidelity tools, things that can effectively run very quickly, but capture the main physics we need to actually do design work. And so in the past, there's been work called what's called Dynamic Wake Meandering. I'll talk a bit more about that. But they were fairly limited. They either did things one of two ways. One's a serial solution where basically if you take it with this model, you can basically model the most upstream turbine, say this one, see what that does on the next turbine, kind of pause the simulation there, run the next turbine in serial and basically march those through the plant. And you can get kind of like a cumulative effect, but you can never in such a simulation say, the downstream turbine can't tell the upstream turbine to do something because it's done later in the calculation. So that's obviously a limitation. The other way these models have been implemented before is they only really look at one turbine. They pick another turbine upstream that really represents the effect of the upstream flow, and they treat it like an actuator disk. And so that's kind of where we started with a few years ago. And so what the objective of this project was to basically develop a new multi-physics tool that really captures the physics we need to drive engineering design and demonstrate that it works and validate that it works. And so what we're trying to do with this FAST.Farm tool is first of all, we need to capture the relevant physics, of course. We can't do that with full up CFD just because we know it's too expensive. We want to be able to get not only the power out of the turbine, we want to make sure we can get the power right from the wind farm, but we also want to get the detailed structural loading of the turbine components so we can do that to estimate fatigue life and ultimate loads and strength and reliability. But we also want to be able to run these calculations in a design loop. Normally, it sounds like you work for DNVGL. Normally, you understand the design process is what you need to do is you have a bunch of load case simulations. Usually, when you're doing a turbine design, you have on the order of 1,000 10-minute simulations you need to run. And normally, you would basically set up these simulations, and if you can get that to run fast enough, so set it up one day, you'll get the answers the next morning. If you can run those 1,000 simulations overnight, then you can tweak the design and make sure you can do the optimization. And, within a few weeks, you have a really nice design. And that's kind of standard industry practice. So I said, can we take that same design philosophy that's focused on one turbine and now do it for a full wind farm? And that's where I'm really trying to tackle with this work. And so what we're trying to do, basically how it works, we rely on some of the dynamic wake meandering principles, and I'll talk about what those are if you're not familiar with that concept. We tried to address the limitations we saw in previous formulations, and we tried to really complement where we had other capability, high fidelity simulations and low fidelity simulations. And we really were trying to use the high fidelity simulations, or the LES simulations, to really drive the physical insight and validation of our mid-fidelity tool. And that's what I'll focus on today. So first of all, dynamic wake meandering. Does anyone know what that is? Have you heard that concept a little bit? So here's the fundamentals. For those of you who don't know, basically, the key idea is we can't full up resolve all the flow because it's just simply too expensive. And so we're trying to say what's really the drivers of the wake and array effects. And really, if you think about it, we treat the flow in basically what's called a split of scales. So we say, well, really the small turbulent eddies in the flow are really what's driving our wake deficit and how that recovers to free stream. We had a nice tour this morning of the fire test facility with the wake measurements and so on. And clearly there's like a near wake effect, vortices that happen, and those get broken down by the turbulence in the flow, and eventually you have some Gaussian deficit in the far wake. And so it's really driven by the small scale turbulent structures that are driving that effect. And then of course, there's also large turbulent eddies in the flow, usually structures greater than about 2D in length scale. And these are what are driving the meandering of the flow. So you can imagine a very, very stable atmospheric flow, these wakes tend to just go straight down, but in highly turbulent conditions, neutral, unstable conditions, these wakes are meandering left, right, up, down, and so on. And those are really driven by the large-scale structures. And so what we're trying to do here for the evolution problem, we basically use the small-scale eddies. We basically solve a very simple RANS solution. We solve it in axisymmetric coordinates, and we solve it in effectively a steady state sense to get basically the effect of the wake deficit and how that evolves with downstream distance. But then we take that sort of quasi-steady solution and we meander it left, right, up, down axially based on the large-scale structures in the flow. And that meandering, so the impact of that wake deficit meandering back and forth is what's really driving the loading of the next turbine in the wind farm. And then, of course, the other thing that happens is as the wake breaks down from concentrated vortices to more uniform turbulence, there's basically an added turbulence effect that happens in that process. So here's our FAST.Farm code at a high level. Really, for those of you who are familiar with FAST, it's a very modular architecture where we try to represent physics in various blocks of the solve and then have what we call a driver that couples all the physics engines together. So we base this tool fully on the modularization framework of FAST, and I'll talk a bit about that a little bit more, but that's not really the focus here. Basically, for those of you who are familiar with FAST, basically that's a single turbine simulation, covers the aeroelastic simulation of the wind turbine, so aerodynamic structures, control of one turbine. We basically have that now as a module within our WIG FAST.Farm solve. And so basically you say, how many turbines do you want in the wind farm? 10, 20, 100. You dynamically allocate that and make a turbine model for each turbine you're interested in. We also have a block that's the supercontroller, which really that's the wind farm level controller, so it communicates on a time-step basis with what the individual turbine controllers are doing. And then, of course, really the new physics in the model is, first of all, we have a wake dynamics engine that's really trying to predict what happens behind one specific rotor in the farm. And we'll talk a bit more about that. And then the ambient wind array effects, that's really trying to drive the full flow across the entire domain. And it will take the individual wakes and move them around. And whenever you have sort of overlapping wakes, it will figure out how to merge them together. And so some of the novel innovations that we introduced here relative to what's been done in previous formulations. First of all, when we do ambient flow over the entire wind farm, in addition to having a very simplistic, what we call synthetic wind generation, we also basically allow the user to specify a full large-eddy simulation precursor domain. So without modeling turbines, those simulations take on the order of a day to run. So just fairly coarse grids flow over the domain to get the right turbulent structures for whatever atmospheric condition you're simulating. So you can run those again in about a day. And then the idea is basically if you create a database of these sort of wind conditions for your farm, you can then, with FAST.Farm, take that flow and actually embed the turbines and the wake array effects and do the actual wind farm simulations quite quickly, but all based on the same sort of background flow. Another thing we've done novelly is we've improved how we do wake advection, deflection, emerging. I'll talk a little bit about how we do that. We've the first ones to introduce a supercontroller within one of these engineering models. And then the other thing we've done is we've solved the entire solution in parallel. So imagine if you have 10 turbines in your wind farm, we basically solve each one of those on a different core of our computer to solve that quite quickly. So whatever the simulation time it takes to run fast, usually that's a real-time effect. Going to FAST.Farm is not much more complicated. We have real time for every turbine, and then there's a bit of a delay when we do this calculation here. But because we're doing it in parallel, we can effectively run just slower than real time. The other thing we're doing is we're focusing a lot on how can we best improve these models through the use of high-fidelity simulation. So constant interaction with the high-fidelity group to transfer knowledge to these tools.
Can I ask?
Please.
Well, you mentioned the ambient wind model using large-eddy simulation. So you're also able to use measured data in math or something? Or where does the ambient wind come from?
Right. So we have, I'll get to this in a little bit more, but basically we have two options to specify the ambient wind. So when I mean ambient, I mean no turbines present. So whatever the flow is over the terrain without the turbines there. So we have two ways of doing that. One is through this large eddy precursor. What you normally do is you You create a periodic boundary condition. Hank could probably go into great detail how this is done, but you basically have a periodic boundary condition that you basically recirculate the flow over the domain, and you, by having certain pressure gradients or thermal gradients, you can derive specific conditions. Whatever shear you want, whatever turbulence density you want, whatever length scales you want in the flow. So we can create those inflows and feed it into this software. The other option is a more synthetic approach. If you run FAST or Blitted, you're probably familiar with like TurbSim or the Mon model. These are very like synthetic by the sense we construct turbulent fields based on basic boundary conditions like power spectra of the wind and various components of the wind, coherence, how the wind is coherent across space, and then how the UVW components of the wind are correlated with each other. And so we can create these things synthetically, and those can be done either based on standard formulas, or if you have some sort of wind prescription, where I have a LiDAR or a Met tower, you could actually build a field from those and then feed it into this. So yeah, we can basically handle all the options. The things with the synthetic winds is that normally those fields are usually they can go maybe a couple hundred meters wide, but to do a full wind domain, not really practical for the synthetic. So that's where we need to go for the LES. So stepping through each one of those a little bit, I won't talk about supercontroller much. This is showing kind of what I was explaining at the beginning, where if you purposely yaw turbines, you can steer the wakes away from the downstream effect. And thus, I don't have great plots here, but if you look at the total power of that farm, much more power you can get when you actually purposely steer the wakes than if you simply allow each turbine to run in its optimal configuration. And so what we've done here is they already had this capability within SOFA to do this, so we just simply embedded the same capability into FAST.Farm. So whatever controller you've made for SOFA, you can embed here. On the turbine side, this is my one slide on FAST. For those of you who are familiar, basically, again, we're trying to solve all the physics of a turbine. So we have aerodynamics, we have structures, we have control, and then if there's an offshore support structure as well, like shown in the floating system here, we have waves and buoyancy and mooring systems and all the sort of physics involved you need to actually do design work here. So we have that capability within FAST, and we've simply taken that here as a module within FAST.Farm. So again, basically the total number of turbines and are defined, and how you place them in the wind farm, you define that initialization. And then, of course, we solve these things in parallel, so it's not a serial solution anymore. The other thing that happens, of course, the time scales of wakes are quite different than the time scales of structural response. These are usually on the order of, hertz, 10s of hertz, and so you want to run these at a fairly time step about 0.01, whereas in wakes are driven more on the scale of seconds, and so we have the ability in our solution to basically solve the wake problem, on the order of seconds, and we subcycle at a much higher frequency to get the actual structural loads out of the turbines. Going into a little bit about wake dynamics. Sorry about the wordy slide here. I need to improve this one. Basically, what we do is we solve the wake of each turbine as basically a parallel solve. So we solve these basically separately for every rotor, and then the combination happens through the other module. And so a lot of if you're familiar with the RANS equations, the key here is all in how do you handle the subgrid scale, whatever you're not simulating. And so we have this eddy viscosity formulation that basically takes into account the ambient turbulence condition as well as the shear layer generated by the wake itself to do the closure so that we can actually solve these equations. Won't go into all these details, but basically, effectively what we do is we solve the wake at different wake planes that get marched downstream. And then we also have transient situations where if you say you suddenly step yaw the turbine, because this solution is effectively a quasi-steady state, we basically pass a time filter in there to allow the low frequency effects to be treated quasi-statically. And you can imagine that over time, what happens if you start yawing if you step yaw the turbine, eventually the wake will start skewing because of that. And of course, the downstream wake was shed before you did the yawing, and so that's continuing on its normal path. So effectively, you get this sort of delayed effect, which is trying to capture the real effect of the transient dynamics. But the key here is all in the closure formulation and the eddy viscosity model. We have a number of basically tunable factors within the model to ensure that that wake evolution can be done correctly. And this is where we've done a lot of our calibration work against high fidelity simulations. Then on the ambient wind side, I kind of went through this already. We have both the LES as well as the synthetic way of generating this. So we have in FAST.Farm to make it computationally efficient. We actually have two separate domains. One is a very coarse, low-resolution domain across the entire wind farm. So if you have 100 turbines, the length scale here is usually on the order of about 10 to 20 meters. So you need a fairly coarse flow over the entire farm just to get the right turbulent structures that are driving the wake meandering problem. But because 20 meters is too coarse for a normal wind turbine simulation, we also allow the ability to basically do higher res solutions around a turbine if you really need that physical flow structure to get the structural loading right. And because you can base it on an LES domain, you can also basically intrinsically include the effects of atmospheric stability and complex terrain if you have that sort of condition. So then imagine we have this ambient flow. What we do is we take these individual wakes we generated before and basically superimpose everything together. The superposition is fairly sophisticated in that the axial superposition basically happens through what's called a root sum square approach. Imagine if you know what a root sum square does, the first sum will take it down quite a bit. And as you get further and further, it's basically some asymptotic limit. So it never approaches zero or goes negative, which is the downfall of a lot of previous methods. And this basically conserves conservation of mass. And then for transverse things, we do a vector sum, but I won't talk about that. This is a high level trying to show how effectively this solution works. So basically every turbine, we generate the wake deficits as a function of downstream distance on these what called wake planes, which are the blue lines here. Each turbine has done that. This low resolution domain is what we have ambient wind data on this sort of yellow gridded box. And then like I said, optionally you can have high res domains around the turbine if you really want detail into the rotors. And so basically we know the deficits on each one of these rotors, each one of these wake planes, excuse me. And then to meander these around, well, maybe step back to do a superposition. So wherever we have sort of the overlapping effect is where we do a superposition to capture the merging effect of those wakes. And then to move these things left, right, up, down to really capture the meandering of the flow to impact the loading of the next turbine, we do what's called spatial averaging. So we'll basically sum up all the velocity, basically the full velocity field, including the wake along each wake plane, and that will lead to some average direction that plane would naturally want to move in what's called a passive tracer idea. And we basically do that to move these planes around. We took a lesson from some of the signal processing world, and we found out that if you do a nice spatial average, like a uniform averaging in the spatial domain, what happens in the frequency domain is you basically get a nice transfer function that looks like that. Not really what we want. What we really want is a nice, basically low-pass filter. We want to capture, again, these large-scale structures, low frequency, that are going to meander this wake around. And this is not really a very ideal filter if you look at a nice uniform spatial averaging. So what we did is we said, let's flip this thing around, essentially. If I spatially filter with this weighting here, then in the frequency domain, I'll get a nice idealized low-pass filter, which is what I really want my wakes to meander around. So that's what we do, is we allow the user to basically apply weightings based on what's called a Jink function in two-dimensional plane, and then we get a nice proper filtering we want in the frequency domain. This is showing an animation of what this thing looks like. So I have, this is just showing one turbine, but it does yaw, so it gets a little interesting. So here I have my LES background grid that I pre-generated. And then here's where I basically embedded my FAST.Farm solution. So I have one turbine here. I'm just looking at a top view here. While the wake deficit is really an axisymmetric solution, fairly idealized because it's embedded on a background flow, you do get all that sort of turbulent nature that happens. And of course, because large-scale structures, this thing is also meandering up and down a bit. You see it is fairly discrete. We're really not resolving the full flow problem. But the nice thing about this simulation is it's effectively real-time or faster. So it's very, very computationally efficient, which is what we're aiming for our analysis. But you see at the end, depending on how far you propagate these wake planes, there can be fairly discrete edge there. So that's all based on how much you want to go. You can propagate that thing farther if you want it to fully decay away before you stop it. What I did there is I simply yawed the turbine now. Basically yawed at 10 degrees, and I think I yawed at 25, and you clearly see the deflection of the wake starting to form from that. So we capture those effects within the formulation. Right. So I won't talk about this much, but basically we developed a nice process. Said, well, for this one turbine case, we want to make sure that we can get the right wake effect behind the turbine. I want to make sure that this model that's much more efficient than a high-fidelity LES simulation can match that LES simulation for what I care about. So what we did is, like I said, there's about 20 parameters, and most of those have very little effect on the solution. In the end, there's probably only only on the order of 5 or so that really make a difference to the solution. So we have these parameters, though, and I want to make sure that they're tuned properly to match the true high-fidelity simulation. And in research, you can find sort of what other people have estimated. So we use those as our default parameters. So what we did is we identified a number of calibration cases. So these were the cases we ran. About 9 simulations in here showing different atmospheric stabilities, all at 8 meters per second, and then different fixed yaw errors as well as a step yaw event. These kind of represent different stability classes of wind conditions, but all at 8 meters per second. For these 9 cases, it took about 6 months of work to generate the SOFA simulations. So that's obviously, I trust those as very good benchmark solutions, but obviously completely impractical for any sort of design work. 6 months to do 9 cases is kind of, I don't know what you're running, Hang, but you're probably familiar with this sort of idea. I can't run more, it simply takes too long. Give me more horsepower. So that was our benchmark. And what we did is we ran about, on the order, I think in this case, about 20,000 FAST.Farm simulations where we simply varied these parameters and basically did what we call a sequence grid search to basically optimize these, what best of these, if I look at a full range of these 20 parameters, what parameters best give me a match to our SOFA solution. And so what we were comparing, first of all, is the wake center, so the wake meandering position. That's maybe a little tricky to calculate out of an LES solution. We have some nice tools that try to look at cross sections of the wake and figure out, roughly, if I time average or azimuth average that thing, I can figure out, what's the deficit profile look like, and also where's that wake center move over time. So by carefully post-processing our SOFA simulations, we can get that sort of effect out. So that's what I'm looking at: wake deficit and meandering statistics out of the solution. So like I said, we did this process because there's 20. We couldn't do a full up grid search. We did a sequence grid search, and this is the sequencing we did here. But there's a nice paper that explains that process, and it's a fairly automated thing now. So if you have a given benchmark where you really want FAST.Farm to match that case, you can simply run this process and it will change the calibration parameters for you. I won't talk more about that. What I'll focus on now is the validation. And so what we did is we said, well, now that we have these calibrated parameters, I calibrated them for these 9 cases. How do they work if I start deviating away from what I calibrated? So are they fairly robust? Do I need to start tweaking these every time I run the code, which would be a real pain? And so what we did is we came up with these 6 cases. What we did is we varied things that we had not varied before, so with different wind speeds, different thermal intensities, different yaw settings, and also looked at multiple turbine situations and said, well, if I simply leave the calibration parameters fixed, never change them, how do my results compare to SOFA? And that's what I'll show here. Yeah.
Sorry, this is more from an electrical engineer
Please.
perspective. If I were more the user of this, is this would I be, if I deliver these parameters, like turbine intensity and speed, is this basically sufficient to set up some common simulation cases, or do I need a vast, more? How much can I boil this down to make?
Right.
Make it be realistic?
Well, you can rely on the experts to generate the wind for you if that's not your specialty. Again, the idea is to basically have a database of flow that then you can do your turbine design work. So that database is like a pre-step. You set that wind up, whatever conditions you need to simulate, and then the actual wind farm simulations are efficient and only require the use of FAST.Farm. But to run the full up, all the capability of FAST.Farm, you need a fast model of your turbines, you need structural aerodynamic properties, all these sort of things. But yeah, so it's really a multidisciplinary thing, but obviously as an electrical engineer or whatever, you want to focus on the controller or the grid interface, whatever it is. it's likely a team environment would need to set up a full-up model, unless you used one of our existing baselines and just tweak that.
Can I just follow up? When you say
Please.
database of flow, are you saying you pre-generate the results in a sense, and then you would look them up?
I pre-generate the inflow, meaning so without the wind farm there. So just what the flow is. And this mimics what you would do in a wind turbine simulation, like for loads analysis for one turbine. What you do is you pre-generate, you run TurbSim, familiar with that. You simply generate wind data for lots of different wind speeds, different turbulence conditions, different shears, whatever it is you need to simulate. And that this database is used basically forever for every turbine designer going through that matches that set of conditions. So this is basically the same idea, but at the farm level. But yeah, so the inflow, though, is basically a pre-step. It's uncoupled from the FAST simulations. It's a one-way transfer of data. Okay, so again, the objective of this is really to really show where FAST.Farm functions well and where perhaps we need improvements in the future. So I'll step through some of the results of the validation. So this is really now the meat of the talk, I guess. The rest was more the background for how we're getting here. So first of all, I'll show some flow viz, just so you can see some ideas of what this looks like. What I have here is, this is for a 8 meter per second case, 6% turbulence density, and a yaw angle of 10 degrees. This is showing the SOFA solution here. So that solution took about 2 weeks to generate. And this is the FAST.Farm simulation that takes about real time. So obviously, what we did is we used the same precursor flow. So the background flow before the turbine is there is the same. And you can see that here. If you kind of look away from the wake, here's a nice higher speed region, which you also see in the FAST.Farm case. So the background flow is the same. The wakes are obviously done very, very differently. This is actually resolving the wake, in the simulation, and this is using our approach within FAST.Farm that I just talked about. You see a lot of common, the mean deflection is very similar. The deficits on average are the same. Obviously, there's a lot more structure that we're missing in the SOFA solution. This is showing the free turbine case. This is at 8 meters a second and a low TI case. 3 turbines, again, mean deficits look very similar. Obviously, a lot more detail here. And what we start to notice is as you lower the TI, the differences become more and more dramatic. So low TI is certainly a trouble for our solution. The other thing you clearly see in our FAST.Farm, again, there's discrete stops. We propagate those planes down a certain distance, and then we simply ignore them. You could propagate them farther. It just simply takes a little more expense. The key here is when you run FAST.Farm, you want to make sure you don't stop the wake, right at the intersection of the next turbine. That may be causing some problems. So you have to be careful of that when you run the FAST.Farm solution. So that's more, qualitative. Here, sort of one more set of qualitative. These are looking at cross sections. What do we got? 2D downstream from the first turbine and 2D downstream from the second turbine. So this is behind the first turbine. This is behind the second turbine. This is showing the case at 10% turbulence density, and this is at 6%. So at 10%, it's really hard to distinguish which one's SOFA and which one's fast. The higher the TI, the more things are driven by the background flow, and we capture that effect within FAST.Farm. As you get to lower and lower TI, so this is 6% TI, behind the first turbine, it's quite good, but behind the second turbine, what we see here is the wake is much more complicated in SOFA than it is in FAST.Farm. And this is because the breakdown of the wake that's naturally happening in SOFA, we don't capture nearly as resolved in FAST.Farm, and so it looks a lot smoother. So this is one thing that kind of stands out as we go forward, is that as you get, again, lower TI, FAST.Farm starts to diverge away from SOFA. Luckily, the low TI case is perhaps less interesting overall, because it's where it's much more uniform flow. It doesn't happen as often, and it's not driving fatigue nearly as much. So now looking at more quantitative results here. First of all, if you're ever looking at wake effects, you want to make sure your thrust is right. If the thrust is wrong, the wake is always going to be wrong. And so that's the first thing we need to check between SOFA and FAST.Farm, is that the wake matches. So we are using the same, again, ambient flow, and so you'd imagine the time series would match quite well. Nicely, we also get statistically very, very good, not only the mean, but also standard deviation, even the skewness of that distribution we get well out of the code. This is showing the wake effect for, the thrust for the 3 turbine case. So this is the first turbine, second turbine, and third turbine. So again, maybe a small mean offset there, but even down the farm, we get the reduction of thrust because of the wake effects. One interesting thing is the upstream turbine really capturing the phasing of all the effects, but downstream, while the statistics look quite decent, the phasing gets a little messed up because of the breakdown of the wake is a bit different in SOFA. Now we're looking at generator power. This is for a case, the same 3-turbine case I showed before with thrust, and this is showing a case with yaw offsets where I've actually purposely yawed the turbine plus or minus 10 degrees for these turbines here. Here, again, the power, quite good statistically, not only get the means, but also the standard deviations, maybe a little bit of offset, particularly as you start yawing the machines. And I can explain why we get that in a later slide. There's maybe a small mean offset, again, likely because our calibration parameter is not perfectly set for this case. These are showing speed and torque, mostly the same effect as I saw before. If you start looking at more wake details now, what I'm showing here is a case with one turbine and a yaw angle of 10 degrees, 8 meters per second, 10% TI. What I'm showing here is basically what the wake meandering looks like. This is the horizontal meandering, so left, right, where the wake center is as a function of downstream distance at a given time. Sorry, this is a function of time. So this is at 2D, 4D, 6D, and 8D. So this is as a function of time what the wake is doing. So this is horizontally, and this is vertically. It's very, very interesting that we capture this wake meandering very, very well out of FAST.Farm. So it's really this passive tracer mentality where these large structures of the flow that push that wake around really capture that effect well with our FAST.Farm code. We even capture the extremities of the wake in the meandering. There's maybe some small offset in vertically, like the statistics seem to be right, but there's perhaps a small offset vertically, and we believe that's because in SOFA what's happening is the wake tends to want to speed up naturally over top of over top of the turbine and push a little faster up higher, and what that's doing is keeping the wake from going as high in SOFA, and so we have a small offset because of that in FAST.Farm. These are showing, so those were time series comparisons. This is showing the statistics of those cases for a 3-turbine case, and so what I'm showing here is basically imagine the turbine here, and then we're looking at 2D, 4D, and 6D behind that first turbine. The next turbine's blocked out. It's really kind of weird to look at the wake meandering right at the turbine, because that's where in FAST it's basically a direct superposition that starts to happen, and it looks a little strange if you look directly at the wakes, but that's not really a big problem for the overall solution, but it basically blocked that part out. So this is looking at 2D, 4D, and 6D behind that second turbine, and then 2D, 4D, 6D, and 8D behind the third turbine. So this is the horizontal meandering here, very, very good statistics. This is the vertical meandering. This is that small offset I talked about that we're not capturing in FAST.Farm. FAST.Farm says, well, this is a nice vertical rotor. The wake just wants to naturally, on average, go straight down the center, but in SOFA it tends to want to move a little bit more. And this is the case with low TI. So this is high TI, 10%. This is a low TI case. Included, there's a bit more differences here, and this is again because the actual wake breakdown driven turbulence tends to be fairly large relative to the ambient turbulence. So high TI tends to work quite well. The lower TI, we start getting differences. Finally, what I'm showing here is the wake deficit profiles. And so what I imagine, what I'm showing here is in the meandering frame of reference. So imagine 0 is basically the center point of that wake, but of course that point is moving around in space. What I've done is in SOFA I've simply time averaged, so about that wake center that's moving in space, I simply take basically the azimuth average of the condition around that moving meandering point, and I'm showing here the axial deficit in that space. So this is basically the wake center. Imagine at the hub, that would be the hub point, and the tip is at 0.5, and this is going beyond. So as you get farther and farther out, you basically get eventually to ambient conditions. Again, I blocked out the condition right at the rotor, which is a little strange to look at, but show 2D, 4D, 6D behind the first turbine, 2D, 4D, 6D behind the second turbine, and then finally behind the third turbine. So first of all, what you see is the hub effect. This is the low TI case, this is the high TI case. At low TI, the hub effect is very prominent. So there's no thrust obviously right there at the hub. And you see that here, but as you get to higher TI, the wake deficit is kind of smoothed out a lot more. It's broken down a lot more by the ambient turbulence, and we get that difference in the FAST.Farm solution. And then of course, as you look farther downstream, we capture the recovery of the wake quite decently in the code. Biggest differences you see are in the lowest TI case, again, because of the effect of the vortex breakdown. I've looked at these in a lot more plots, and these are just kind of the basic conclusions we've had from our studies so far. So in general, we feel like we're capturing the right statistics of the power, torque, thrust, and speed. So not only are we getting the mean effects, which is what you'd get with a steady state model, but we also get all the statistical properties about the mean. We're capturing the horizontal and vertical wake meandering very well out of our code, and these deficits are also quite decent. Or where we miss, where certainly FAST.Farm has its limitations, is on some of the finer wake details and wake asymmetry that we see out of SOFA. Certainly the near wake effect is not captured very well. The FAST.Farm model is really tuned to get the far wake accurately, but obviously the vortex breakdown that was being measured by a colleague here in the wind tunnel is really not captured. That's really important for getting the loading right on the turbine, not so much the far wake effect. And so what we really think is the ideal solution would be to have a nice vortex method for the near wake and transition that to this Gaussian model for the far wake. And that would be, I think, the ideal combination of models in this sort of engineering sense. We capture well for high turbulence, but for low turbulence, we start seeing more differences. I mentioned that before. The other thing we're not capturing, we capture the deficit very well, but things happen in a full wind farm, like I mentioned, the flow either going over the top or around the sides of the wind farm where flow tends to speed up. That part we're completely missing in our code, and we have to address sometime in the future. The other thing that is not a big study in NREL is what's called curled wakes. When you start skewing the flow purposely, it's not simply a shift of the mean center line, but we get these basically counter-rotating vortices that happen because of that. We want to make sure we capture that effect, which is important for the power and loading of the downstream turbines. This is why the lack of this is why we feel like we're getting a bigger mismatch for the yaw cases. That's about all I have. So where we are going now. So we have a number of sensitivity studies going on at the moment. We want to basically assess, full LES precursors versus a very simple synthetically generated flow. Make sure those match where they should, and also just see, what's the assumption of doing a much more simple synthetic type flow. The other thing we'd like to do before we release FAST.Farm publicly is really assess the full spatial temporal resolution sensitivity. Right now we've tried to run a fairly fine resolution in FAST.Farm just to ensure we're capturing the terms right. But we want to make sure we can go coarser and basically provide guidance on how coarse can you go, which will then obviously speed up the code a lot. So we're trying to give guidance to the user on how to choose resolutions. Then we plan to make FAST.Farm public, and that's coming likely this fall if you guys want to start playing around with this yourself. And then the other thing we're working on is validation with real-world data sets. So the only thing I showed you today was against high-fidelity LES, but we're doing comparisons against this OES wind farm. That's the SOFA simulation I showed on the very first slides. The 36 Vestas V90 turbines. We have a really nice data set of wind and power, as well as structural load measurements on 2 of these turbines in that farm. So we're using that data to validate the tool. We also have data from low-grade wind farm that has power and loads. And then within this IEA Wind Task 31, there's a nice benchmark based on what's called the small SWIFT experiment. So for those of you who are doing any sort of wind farm simulations, whether these type models or high fidelity, this sort of IEA SWIFT benchmark is a great way to do that collaboratively in a group. So if you're interested in learning more about that, I'd be happy to give you information on how you can participate. Industry has been very excited about this new capability because they have a lot of, mentioned earlier, there's a lot of codes that can do one turbine very well. But the wind farm effects are quite minimal in industry. And this because this is kind of expanding what's been done in the past. and also is very, very efficient. We've had a lot of industry interest, and so I have a number of projects where we're working directly with industry clients to do, model improvements or validation studies for their specific technologies. So I'm very excited about that. That's the whole point, is making sure we can improve what industry is doing. Controls people, this wake steering is a huge thing, like I mentioned earlier. But the question always when you start steering wakes is what happens to my loads in my wind farm? Usually the question is always some gray area. Usually some loads go up, some go down, but really need to understand that well. And so all the work that's been going on right now with Flores, they've basically been spot checking, only running a couple cases in SOFA just to see what happens with loads. But now with FAST.Farm, they basically plan to somehow integrate that knowledge into their control loop processing. During the introduction this morning, I talked a little bit about offshore, and so that's another huge area. So I got my PhD studying floating turbines, so this is a fun area for me. And I'm really curious what happens in the wind farm setting. So if you have a nice turbine on a floating platform, it's not now rigidly attached to the ground. It can move because of the station keeping system. It can drift and yaw and so on. So what happens now if I have a wake coming in that's not just uniformly hitting my turbine, but partially hitting my turbine, it will induce a yaw moment and start moving those turbines around. I really think there's a lot of interesting, as a researcher, a lot of interesting questions that can be raised. What happens in a wind farm setting for floating turbines? And then what can you do with that? Control or mooring system design or whatever it is. That's a whole new area, I think, that'll keep us busy for the next 10 years to study. So that's a fun area that we're going to start getting into. Then finally, what I really see in the end is you're not going to throw away high-fidelity simulations. You're certainly not going to throw away low-fidelity simulations. What I really see is it's a multi-fidelity world, and we need to apply these tools in some combination that best makes sense. And so I showed clearly how you can calibrate this model to match high-fidelity results. I think likely what you would do in a real setting is you probably pick a few critical cases. You calibrate the model to make sure it works across those cases. So you're running, on the handful of high-fidelity simulations, you're running, thousands and thousands of FAST.Farm simulations and probably millions of low-fidelity simulations. And using a combination of that, you can do really cool things with, of course, to validate the models. Uncertainty quantification, you really want to understand not just, does it match here and here qualitatively, but really, statistically over the lifetime, do these things really match? So we can do cool stuff with UQ, and of course, doing design optimization with these models is one of the next steps. But with that, happy to answer questions. Otherwise, I always like to say carpe ventum, which, for those of you who don't know, that's seize the wind. That's my motto. But yeah, I'd be happy to take any more questions. Thanks.
I'm curious, what's the when you talk about the benefit of it, is it more that you're steering the velocity deficit away from the turbine, or is it more that you're able to sort of create a channel where you have the speed up around the wake? So you're actually getting some sort of speed up effect there. Maybe it's an artificial distinction in a way.
Right, exactly. It's probably semantics, but yeah, effectively, that's not a great pen, is it? So yeah, if you take the standard case, I didn't have a good picture, sorry, but normally you'd say, well, the power of this turbine's here, and if you look at down a row, what happens is, usually goes something like this, so it drops off really, really quick. Second turbine's, about half the power, say, of the first. But if you simply yaw that turbine slightly, then this wake essentially starts skewing like this, and then while this one goes down a bit, this one's way up, and so the average overall is a huge benefit. And so what they're effectively doing is they're staggering. So this one's this way, this one's this way, this one's this way, and what that effectively the wakes are up, down, and effectively missing the turbines, and so you're not getting that power on any turbine, but overall it's quite a bit of a boost over the other. And it's both the deficit itself as well as it's fast, the speed up effect. It's really the deficit I'm capturing in FAST.Farm. The speed up effect usually tends to be more what's called like a blockage, the wind farm blockage effect. It's really seen on like a huge wind farm, like if you have a bunch of turbines in the farm. What tends to happen is the flow kind of accelerates around the side, and it's that and so usually the corners get quite a bit more power. And this is also an effect I mentioned in FAST.Farm. We focus really on the deficits, but the speed up is quite important. As the farms get bigger, the speed up effect is more important, at least on the edges of the farm. Good question. Yeah.
I'm just a bit curious about wind farms. Does the factor called global warming and climate change affect wind energy in a huge basis? Like, can we like modify? I mean, is designing of wind farms going to be affected due to these changes in global warming and climate change? When you look at the future, like, can we have some kind of flexible designing, like, which can be modified in the future?
Right.
Just a curious question.
I mean, I'm maybe not the expert on that, the climate effect, but I mean, likely what's going to happen is, right, the wind patterns are going to shift. So what used to be a good wind resource may not be so in the future, but another site is likely going to, the wind's not going to suddenly go away, but it'll probably shift locally. And it's probably it's a regional decision that probably has to be made. But in terms of estimating what that will look like in 10 or 20 years, yeah, it's beyond my capability. I'm sure there's experts that can answer that better than I can. But yeah, that's a good question. So the other question is about storms, because storms tend to get more. That's certainly been shown, with big hot discussion in the U.S. with anti-science versus science people, and certainly I'm certainly on the mindset that the storms are simply going. I mean, the water is simply that much warmer, and the storms are going to get worse. And so, I was at this conference, oil and gas conference in the in 2005. It was right after the big hurricane that went through New Orleans. And so all the oil and gas presentation guys are like, I've been measuring, I have 50 years of data. If I look at this storm, it's way beyond my statistical extrapolation, right? 100 years, and the oil and gas, these are executives, like, I'm not saying it's climate change, but statistically, this is a big anomaly here. And if I look at the past storms, it's getting it's getting more, it's more severe. And so I think, I would say there's certainly enough both scientific evidence as well as practical measurements that are showing that certainly storms are going to get worse. Yeah.
We're going back to FAST.Farm.
Please.
Just to have a bit of a better idea of the computation efficiency, you said real time that would be for a couple of wind turbines.
So it's real time for however many turbines. So right now, the only limitation that we have is it's an OpenMP parallelization. So if you're familiar with these parallelization concepts, OpenMP is like one node, and whatever memory and how many cores you have on that node, you can do real time on that. If you need, and right now we're limited by that. And so if you have 1,000 turbines, I probably don't have a processor big enough to handle that case. So we need to eventually go to an MPI sort of parallelization. Right now it's an OpenMP. And so it's really simply limited by how many processors you have. So if you have less turbines than you have processors on your node, you can certainly run real time. But if you have more,
the number of cores and memories that you've been working with in these examples, roughly?
So these examples here were actually just run on this machine. It has 4 actual cores and 8 virtual cores, and so 3 turbines, no problem. And of course, I mean, you can get with right, or you can get 8 turbines. I didn't do it, but yeah, I mean, you can easily buy systems with 24 cores or whatever, and so doing sort of these mid-scale wind farms, you can do on simple computers. What we need to start doing very, very large turbines, hundreds of turbines, and we'll need to do like an MPI. We simply haven't gone there yet, but that's in the future plans. Right?
Yeah, so in that vein, then, I mean, you would use this in real time to determine how to yaw your turbines, potentially to steer the wakes. So you would actually
Or look at loads, and steering wakes is obviously one research area that we're doing, but the other idea is simply, what's the actual wind at your turbine, not some. The industry practice is usually what's called effective turbulence, where you design it for a given wind class, and then you scale up. When you do your site measurement, you simply take the measured wind and you scale it up by some effective factor, and that's what your turbulence is when you do your siting and so on. With this simulation, we can know actually what's the real turbulence level based on the actual wakes and the meandering that's going to hit your turbine. But
I
so.
mean, I think, but in terms of turbine control, though, I think given what you said about wake steering, I'm just wondering how you would go from this model to actually using that to control your turbines, because you have so many different scenarios like, the wind shifts a little bit and the geometry of the farm has changed. I mean, the turbines are in the same place, but, relative to the wind, turned a little bit, so.
Right. So I would say it's probably just along the lines as you would do with a normal turbine controller. You would, you have a bunch of load cases. You want to make sure it's robust across those cases. And so, I mean, right now what they're doing, they're simply running Florus and they're saying, based on power only, this is the optimal yaw setting of my farm, and that's like calculation that just happens like this. But there's completely no load estimation in that calculation. It says this is power optimized. So the question is, if I start looking at those different yaw arrangements and start actually doing real simulations with loads, then I can make better informed decisions on what really makes sense. Likely it won't be like a real-time active. At least not yet, I would imagine. Right now it's probably going to be more statistical, like I'll keep the yaw setting for this length of time, informed based on some numerical analysis like this. I won't be actively yawing time step by time step to try to maximize, at least not yet. So it's probably more, I mean, this is how typical yaw controllers work as well. They basically work on 10-minute cycles. They're measuring, they're integrating some yaw error, and as soon as you hit some threshold, it will yaw the machine. The actual yawing actively real time is, creates gyroscopic moments, and it's just generally a bad thing to do. So this is more of a quasi-study thing. Good question. Yeah.
Really interesting idea with the diagram here. Do you know approximately how many wind turbines you'll need to offset the loss from the first wind turbine? There's just one.
Even two turbines, you see it. So, yep. Yeah.
Is there a reason why 6 and 8 meters per second were chosen? Seems a little on the low side.
Right, and this is probably because of where the controls people are focused on. I mean, if you look at wake steering is really useful below rated wind speed. So above rated, you're really trying to just shed load. You're already at max power. It won't look like this at above rated. It will, even though you're in a wake, the wind is still high enough that you're still in full load region. So it's really in the below rated, which is where, of course, most of your wind is, if you look at the wind speed probability distribution. So 8 is like the standard, normally, obviously, in a real design, you want to look at probably 6, 8, 10, and different winds. And here we just focused on the midpoint.
But you don't want the higher wind speeds for structural results on the downstream?
For loading, I completely agree. You have to look at the full range. But for power, that's less interesting for control setting. It's simply, the goal there is to simply shed the load, because your power, you're already at max. Right.
There's the NREL 5 megawatt benchmark turbine.
Right.
And I don't know, but I guess this is probably one of the things implemented in FAST, I guess. What's the future? Is there going to be, there's a 10 megawatt benchmark from Denmark, or is there going to be some other benchmarks? Or
Right. So that's been a very common thing going on right now. So I was actually responsible for the NREL 5 megawatt about, what was that, 13 years ago or so, and that took off way beyond my. When we developed that, and it took off and became very crazy, it was like, wow, there's this huge need that was basically unknown and unmet. And so since then, there's been a number of developments, and really the NREL 5 megawatt was more of a, let's just look at existing data and let's kind of make a composite best information at the time. What's going on now is much more, let's use our system engineering tools, design tools, and actually design baseline turbines at different ratings. So within IAA Task 37, there's this 10 megawatt DTU reference. This is probably the one you've been talking about. They've been updating that recently to make a more representative 10 megawatt based on current knowledge of design. And so that probably become the new benchmark of that sort of large offshore scale. We also feel like we needed one for land-based applications where 10 megawatt is just way too big. And so there's also been a development of a 3.4 megawatt baseline machine. So I imagine both of these two will probably take over what the NREL 5 megawatt used to do in the past, become nice benchmarks for all the students doing studies on new technology or control or wind farms, whatever it is. So yeah, but I can send you links if you need more information on those turbines.
Now, can you let me know more about the uncertainty quantification you mentioned in the very end? The reason I say that is because the model have a number of components. You have aerodynamic component, you have fatigue component, you have stress component.
Right.
And each model have its own parameters. So when say the fatigue lag is not correct predicted, and you want to go back to find out where is the main cause of error before you actually fine-tune the parameter, then you go to the uncertainty quantification. So what is the method?
Yeah, so I mean, the way we're tackling it now, so I have another project I didn't talk about here at all, but first of all, the first thing we wanted to do when we start looking at uncertainty quantification is, if I look at full up distribution, the probability is a bunch of inputs. If I have 1,000 inputs, what do I do with that? That's too much. And so the first study we're doing, that's what we're finishing up right now, is so if I look at all the things that can drive uncertainty in the output, what are the top uncertain? What's the most important? And so what we're doing right now is effectively a sensitivity analysis to say what in the inflow, so shear, veer, turbulence intensity, length scale, coherence, Reynolds stresses, all the things that can go on inflow. What of those things actually matters to things that I care about, ultimate loads, fatigue loads for operational turbines. What we've done is we've parameterized all the input. We ran about 50,000 FAST simulations. We fed it through. We said, well, based on the range of possible inputs, which ones of those are driving the outputs in the most sensitive way? Basically looking at the gradients and saying, what's the most sensitive? And so from all my huge number of parameters, I can narrow it down to say, well, the top 5 are these, the top 10 are these. And if I know those, then I can do much more cool things with joint probabilities of those things. Look at the brute force ways like a Monte Carlo. There's polynomial chaos expansion and so on, all these sort of other ways you can start propagating that through. But we're first focused on sensitivity. So what are the most important parameters? We've done that for the inflow, and the other one we're finishing right now is on the turbine side. So I say, what's the unknowns of my turbine? Aerodynamic profiles, that's probably the most uncertain, lift and drag. Obviously, it in a 2D sense, wind tunnel, but in a spinning environment, it's very much uncertain. Structural damping is another big one. Like I always just assume some number. I don't really know what the real answer is, and so what's the sensitivity of that? There's stiffnesses and natural frequencies that may be different and so on. So what we're doing now is we parameterized all the, of the 1,000 inputs in FAST, we narrowed them down to about 45, I think we're saying is probably the most sensitive, and we're propagating those through to figure out what's the top 5 or top 10, or what's the real break point beyond which they're all kind of the same. And so we're doing that now, and I have a journal publication that we're working on for that to answer that question. So then I can tell you, for a given turbine, here's the top 5 parameters or whatever it is. Here's the for the air inflow, and here's the top 5 or so for the structure that are really driving the loads more than the others. And then again, once you have that, you can do really cool forward propagation problems with joint probabilities and so on. And then the next question is to do backward propagation and design under uncertainty, all those cool things. But we're trying to start off very systematically and say, well, let's first identify what really drives the output, and that's the current focus. We're doing it now for the turbine level, and our next year is to do that for the wind farms. Say, okay, I can know it for one turbine, but in the wake effect, there's probably other things that are going on, and so we're doing that. That's our next study, is basically apply that with FAST.Farm to do identify the most important parameters for loads of downstream turbines.